Got it. All right, so our exponential functions look like this. Where a is our initial amount, it's also our y-intercept. Whatever number's multiplied in front is your initial amount and your y-intercept. The base, what is under here, has to be positive. 100% of the time, absolutely every single time. It can be fraction, it can be decimal, it can be whole numbers, it can be big, it can be small, but it cannot be negative. Cannot. Because if you test it out and you try and graph it, remember our exponential functions kind of look like this. If we have a negative base, it would be here, like, it would be super gross. Gross. It becomes the most chaotic piecewise ever. Do not do a negative base. It is bad. Bad times. Okay? So our base cannot be negative. But we've got the information here about our domains and ranges as well. We'll get into the domain and range when we start getting into our graphing stuff, which if we get there today, that'd be fantastic. But I don't know that we will. So we're going to practice writing some equations. And luckily, you still have your form up there at the top of the page since it's on the same page. So we've got the number of fruit flies triple every 4 hours. And there's currently 100 fruit flies. We're going to write an equation for this situation. And I just dumped coffee down my front. Love that. We love that for me. It's so much fun. All right. So how are we going to start with our function rule? What is our starting amount? 100. That's how many we're starting with. Triples every 4 hours. How can we write that? So I love our instincts there. Our x is going to be in the exponent with an exponential. So if we think about every 4 hours, it's going to multiply by 3, right? Only one else here. If every time it multiplies by 3, every time it multiplies by 3, it multiplies by 3, multiplies by 3, multiplies by 3, right? That's our base. This triple is the base. Because each time it multiplies by 3. If it was double, our base would be 2. If it was quadruple, our base would be 4. If it was half, it would be 1/2. Okay, so whatever it multiplies by each time, that's our base. And if it was every hour, we could just say x, right? Or t. Do you guys remember how we make the adjustment for the fact that it's not every hour? It's every 4 hours. Yes, exactly right. X over 4. Because it takes 4 hours for it to triple one time. So for my exponent to be 1, my x needs to be 4. So, sorry, there we go, zooming in. So since it's every 4 hours, we have x over 4. Okay? So the next one asks us to figure out how many fruit flies there's going to be in 24 hours, which we can do by hand. However, this chapter test, we're going to let you guys use calculators. I cannot make the promise that we're going to have it on the final yet. We haven't gotten it yet from IU. Okay, but for this chapter, because we're going to be getting into logarithms and natural logs and that kind of stuff, and E is gross. E is gross. So for this chapter, we're going to use calculators. Okay? Since y'all have never had to deal with that before, I stashed my calculators behind Surfing Cat, so if they don't have one at your table and you want one, Surfing Cat has the calculators. Okay? So we can practice calculating this using the calculator, or you can do it by hand. Because we're going to evaluate it at 24, when x is 24. So I'm going to do it on a calculator. And this is the same as the yellow calculators there. It's the buttons in the same spots in the same order. And we're going to do our 100 times 3 to the, and if you do not remember our how to raise it to our any exponent, it's right here. And if I move my mouse, you can actually see the button. It's called a caret. It's a little arrow that doesn't have like a stick, but it's right here. It's a little caret. And that takes you up into the exponent. And one thing I absolutely adore about these yellow calculators, second column, third button down, is the fraction button. And if I get out a laser pointer, it'll look like a fraction. And we can put 24 over 4. I mean, we could simplify that ourselves because we're awesome and we could totally do that. But if we get to use the calculators anyway, pshaw. Pshaw. So after 24 hours with the 100 fruit flies, I can't say that, fruit flies, we have 72,900 fruit flies. I have to think so hard about saying all the letters. If I try and say it even 3 times fast, it's gonna be a mess. Shoot, I'm saying it 1 time and messing it up. So it was, and I have 100% forgotten, 72,900. Boop. Flies. We're just calling them flies. Okay. So that's how we do that one. Okay, so you guys have done these before. Like, we've worked with exponential functions. Granted, we spent a whole chapter on them last time, but we're going through it. All right. So let's keep going. Because we're going to talk about the 2 different kinds of exponential functions we're going to have. We're going to have exponential growth, and we're going to have exponential decay. So exponential growth is always increasing every single time. And that happens when our base is greater than 1. So if we think about our exponential form where it was a, b to the x, this base is what decides if it's growth or decay. And our a is also when a is positive, it's growth. If we have an a of, like, then things start to flip and we have transformations and it's a whole deal. And exponential growth in general has a horizontal asymptote. Oh, we still have asymptotes. At 0. And kind of looks like that. And similarly for decay, it's always decreasing. Did I spell? sweet, I did spell decreasing right. I always feel like there's too many vowels in it. Not that y'all can tell how many vowels I have in there anyway, because they're smashed together. And our base here, it's not when it's less than 1. It is between 0 and 1. Fractions, decimals, small, little, so cute. Because remember, we cannot have negative bases. So don't just say it's when your base is less than 1. You cannot have a negative base. Why don't I have an equal sign on either one of those? What's 1 to the first? 1 squared. 1 to the third. 1 to the fourth. 1 to the millionth. So is that an exponential growth or decay? No, it's constant. So if your base is 1, it is a line.
It is a line.
Like it's a straight up horizontal line.
Oh, I thought you said it is a lie.
No, not a lie, a line. Apparently I'm struggling with both consonants and vowels today. All right, so our basic kind of vibe on what that looks like, again, it's going to have a horizontal asymptote. In this form, it is just 0. And it looks like that. Okay, so then we're gonna practice on the next page. Is it growth or decay? And we're gonna read them. Yes, dear. So when our A is positive, it looks like this. If our A is negative, that does a vertical reflection. So if our A is negative, it makes them kind of swap places. So because a negative A, just like on a quadratic, it gives us a vertical reflection across the x-axis. It would flip it here, which would make it be decay. So if your A is negative, it makes things flop. Just like if our A is negative here, it would make this one flop. It would reflect across that x-axis, and we would have a growth. It would just be a limited growth. And we'll look at that in just a second when we're checking to see, is it growth or decay? And this is the one that made me decide I was going to print this out for you, because all we're going to do is say growth or decay, and it would take so much longer for us to write these equations than to say growth or decay. Okay, so we're going to look at our equation. So using our, ooh, chunky marker, holy cow. A times b to the x. We're using mostly the b value to tell. Mostly the b value. Whoop. Go away, blue line. So on this first one, what's our b value? 2. B is 2. So is this growth or decay? Growth. Ta-da. On this one, is it growth or decay? Decay, because it's a fraction. 1/3 is smaller than 1, so it is decay. How about on the next one?
Wait, why is it decay?
Because it's between 0 and 1. The fractions make it get smaller and smaller and smaller. So if our base, the piece that has the exponent, is between 0 and 1, it's going to be decay. So how about this one? Growth. We look at this piece that has the exponent. It is growth. Let's look at the bottom row. These are where it starts to get a little trickier. What about this first one? Decay. That one's not tricky at all, except for the fact that it's a fraction. What about this next one? It's decay. This piece is growth, but it has been reflected across the x-axis. And if I take growth and reflect it, it looks like that. So this is decay. This is a reflected growth. All right. The last one is the trickiest, I think. Decay. Why? It's going to turn into a fraction. This is the same thing as 1/7 to the x. If we bring that negative exponent in, we flip it as its reciprocal. So that one is decay. Okay. Questions on that part? Because now we're going to do a big ol' like, whew. It's still exponentials, but it feels like we've jumped a whole nother section. It's not, but it feels like it. Because we're going to talk about exponential growth in terms of population. And yes. Oh, yes. So it's still the same kind of pieces. If you look at our formulas, we still have a starting amount. We still have what it's growing by, and we're still using an exponent of x or of time. Holy cow, that got microscopic up there. So it's still our starting amount. It's still what it's growing by and time. The only thing that's different is it's not doubling or tripling. It's growing by a %. So we're going to use the pieces in our paragraph here that luckily you don't have to copy down to build these. So we've got the population of Albany, Kentucky, growing at a rate of 2% annually. If the current population is 25,000, what will the population be in 5 years? What is our equation going to look like? A equals 25,000. 1 plus, and then yes, 2% as a decimal is 0.02 to the t.
Is that not 5?
Yes, it will be 5. I was just doing the general equation first. I tend to write a general equation and then substitute in a value, because then sometimes they come back and say, what is it in 10 years? What is it in 20 years? And then I don't have to rethink or go, wait, which one was it? So then, yeah, we're going to absolutely substitute in that 5 that we were asked about. 1 plus 0.02 becomes 1.02 to the 5. And we're going to use a calculator to do that so that it's not gross. Because doing that by hand would be obnoxious. Because we have 25,000 times 1 plus 0.02, or you can simplify it and add it yourself. As long as you put it in parentheses, it doesn't really matter. Raise it to the exponent of 5. Otherwise, we'd have to manually multiply together 1.02 times itself 5 times. Gross. To get 27,602.02008. Where should we round here?
100.
To a whole number. Why? It's a person. If you tell me you have 0.1 of a person, that means into your town square you took an arm and just chucked it in. I think it might affect your population. Don't tell me children don't count as whole people. Don't tell me amputees don't count as whole people.
Yeah, that'd be.
I'm telling you, I've had this debate before. Do not tell me that there's part of a person in your town. It's gonna affect your data. They still count as a whole human. People in the hospital count as whole humans. Okay, so if we're talking living creatures, round to a whole number. 27,602.
What if we're talking about like taxi cab?
27,602. What was your stipulation on that one?
What if we're talking about like a taxi cab? It's like taxi cab.
Taxi cab. Well, if we're talking vehicles, again, we're not going to have partial.
But what if
What's
there's
up?
one manufacturing?
We can use a calculator for this chapter test. Yes.
Bo was not paying attention.
Yes, we can use calculators. Okay. So if we're dealing with money, we're going to round with 2 decimal places. If we're dealing with living creatures of any kind, I don't care how you feel about the living creature. Even if it's tarantulas, even if it's flies, whatever. Living creatures, we keep them whole numbers. It's always slightly terrifying when it's elephants to like the 0.5 and someone's like, it's a half elephant. Oh, it's sure as heck not. I'm just telling you, I have this conversation every time I do exponentials. All right, so then we're going to do a decay. Same vibe, different flavor. Because the only thing that changes here is instead of it growing, we're going to have a smaller than 1 number under the exponent. So what's our kind of generic equation going to be here? Our amount is 23,000. 1 minus 0.15. Do not forget to switch it to be a decimal. To the T. But we are specifically asked about what happens at 3 years. This is genuinely how they calculate the value of a car. So if we simplify this, 1 minus 0.15, this is true. Each car depreciates at a slightly different rate. But if you want to know what your car is worth in another 12 years, you could take what you paid with it. And 15% is kind of an average depreciation rate. But yeah, the second you drive your car off the lot, its value goes thunk. Because it's an exponential decay. But it's never going to be negative. It's got that asymptote.
What was that word?
Say it again.
What was the word you were using?
Depreciate.
That's a good one.
Depreciation is another word for decay. Yeah. It's just that tends to be used in financial yeah. It's a tense of depression. 15% each year. Each year. There, I faced it. Did it do that on yours? It is genuinely a typo, not that the screen got grumpy. So we're going to type it in the calculator. 23,000.85 to the third. How much is your car worth after 3 years? This is why we don't buy new cars. It lost almost 10 grand in 3 years. Do not buy a brand new car. 10 grand is pocket change. Can I have your pocket change then?
Everyone at the school would know.
14, and I have mentally blanked it. 124. And it was 0.8788. Other way. Twice a year.
2 times a year?
Yes.
Oh,
Think about semester
so it could also
cutting the year in half.
buy.
That one can also be used as twice a year. It can also be used every 2 years. So it took.
Oh, you're right.
So it depends on the context. Usually semi cuts in half, and by does every other.
I have the chart somewhere.
but they,
Annually.
yeah. And yes, there is technically a right answer, but colloquially, they are used interchangeably. That just means in common language. Okay, we're gonna kick it up one more notch, because this is just our annual changes. We're gonna go more towards the banking side of things and deal with our compound interest. Aren't we thankful for calculators? Ah.
Like A equals P1 minus R over N.
I will check and see if we give you those formulas, but honestly, I'm not sure. I think yes, you do need to know them. I don't have the actual test in here yet, though. Okay. They build upon each other. They build upon each other. All right, so this has all the same pieces, except I have written this as a decay and gave you a growth story problem, so we'll fix that as we go. Because there's a small typo in here because this is not decay, this is growth. Laura is investing money into a very high yield savings account of 4.5%. So we want to know how much money she has after 20 years. So change the formula on your page to have a plus because she is gaining money, not losing money. She is growing her account. This is an investment. So all the other pieces are the same except for the N, and the N is our compounding unit. How many times per year it's being compounded? Semi-annually is going to happen how many times per year? 2 per year. So when we write this as a formula, we have the amount in our account is our starting amount of $4,800, and we are growing our investment, so it's a plus. Our rate is, as a decimal, what's our rate? 0.045 over 2.
I was just saying.
Yeah, I was gonna say just calling it out. And then our exponent here is gonna be 20 times 2. You have to take your n that you divide your rate by and also put it in your exponent. Has to be, has to be, has to be. Otherwise, you're having your time. I was gonna say there is a right answer to it versus semi versus biannually. However, in the real world, the common folk use them interchangeably. The common folk. I got in the peasants. I got in trouble for using colloquially a minute ago. Colloquially, they are used interchangeably.
Yeah.
So just in common language, in the real world, they're used interchangeably. Indeed, it is. So we're to get our values, we're gonna type these into a calculator. And this is when I love these calculators because we have 4,800. 1 plus, and again, second column, third button down gives us our fraction, 0.045 over 2. You can put it just like this. Exponent of 2 times 20. You don't have to simplify it. The yellow calculators are super awesome and will do it for you. So after 20 years, she has almost 12 grand. Start saving for retirement as soon as you get a job. Because she has less than $5,000, and in 20 years, she has almost 12. So 1168, or 11,688, 91. The only difference over here, what changes over here for compounded monthly? The 2 becomes 12. Boop. And we get 11,786.24. Yes, they should both have dollar signs. It's more important about the balance of the account than the interest rate of the account. Because I just heard disappointment in the amount of change between the two different bank accounts. Yes, dear. Yeah, so our N changed. We didn't multiply by 12, but our N changed to 12. So our account is almost, our equation is almost the same. It's 48,001 plus our 0.045 over 12. And 20 times 12. So our N changed. The amount underneath changed. Okay, we're doing one more like this. And you see it on your paper.
Did you get Jasmine? Did we switch kids?
No. I had her, but she got switched. Yeah, she's in your regular.
Okay. Same kind of vibe. And again, I have a typo in the equation because we're still growing money here. Otherwise, it's not such a good investment. If you invest money and it loses money, that was a bad investment. I mean, you can. That's what the whole stocks are. You can lose money. It's just not a good investment if you do. Okay, so we've got Aaron putting $5,200 in his daughter's college fund when she's born. It's got 3% interest. That is, honestly, that's a decent interest rate on a high yield savings account. How much money will she have after 18 years, compounded weekly and compounded quarterly? So what's our equation going to be? Weekly is 52. Quarterly is 4. So we're going to have our $5,200 or our $5,200. 1 plus, what's our rate? 0.03. 0.03. And this one is compounded weekly. So how many is that? 52 weeks in a year. And we're going to do our 18 times 52. Because it's 18 years. So he invested this when she was born. How much does she have when she graduates high school? Type it in the calculators. What do we have? 85 cents. What do we get if we compound it quarterly instead? And also double check his work because I didn't type in the calculator. over 4, and this time our exponent is 18 times 4. NT.
Oh.
8,905. 905. And 25 cents?
27.
So 27, excuse me. I didn't do it. I'm just going on what you said. And these are all dollars. Okay? So there's really only like 16 bucks a difference.
What's the point?
Well, that's when you look at it, you say, well, which of these bank accounts has the lower fee? Annual rate. Which one's going to cover that difference?
How come 18 times 52 is so big?
It is.
18 times 4 isn't small.
But we cut the percent into significantly smaller pieces for these so big.
But exponents.
Exponents are good, but they only go so far. Okay? So let's talk about our transformations on the next page, and then we will start with graphing tomorrow. Okay? So let's talk through the next page. We got through exactly as many as I wanted us to get through. Yes! I'm so happy we didn't have to write out those paragraphs because you're doing great on time. Huzzah! All right, so let's look at our graphing exponentials and remember what our transformations do. This is going to be the last thing we do. We have seen A before. We have seen H before. We have seen K before. Same guys, same jobs. Always. They work on the graph. So H is in our exponent, just like H is always kind of bundled in with the X. Our H also still has that opposite sign. Isn't it Miss Hannah that does the opposite? The opposite.
Well, I think she was just like, ha ha.
Oh, the opposite. I know there's one teacher over there that goes opposite every time. I'm like, sounds like you're having an asthma attack.
Yeah.
But all it is that it follows the formula. It has the opposite sign there, and H does what transformations? Left and right. It is our horizontal transformations. That's a T. There we go. What does K do? Up and down. That is our vertical transformations. Goes up and down. And that one does not change signs from what's in the expression. It's exactly what we think it's going to be. Added on the end over here. Boop. All right. A, what is its job? Yep. So it's stretch, compress, or reflect. Be more specific on our reflect. Over the x-axis. Reflect x-axis. I don't care if you say over, by, with, whatever, which preposition you choose to use. Because of reflect x-axis. Ka-chong. I don't know. I'm in a mood.
That's the sound of being reflected.
I guess. Okay, so B is our base. And for the most part, it doesn't do a whole lot. But you can also think of it as when we have our fraction base, is it does a y reflection. So if it is 1 over 2, it's the same thing as 2 to the x with a y reflection. If our base is a fraction, it does the same thing as a y reflection. That is 0 less than b, not duck b. Kind of looks like a bad duck. Okay, we will start with graphing these tomorrow. We are going to get through this whole packet this week, so bring this back. These are our notes for the week. This section of what we're going through is actually 2 sections in the book. But it kind of blends it together. That's why it feels slightly chaotic when we do it, is this is a more logical progression than the way the book does it. I don't care if you do it on 1 paper or 2 papers, but it is 2 sets of questions. Okay? So we're going to be working with graphing and we're going to be working with solving tomorrow. Have a great rest of your day. See you tomorrow. Bye.